to quantum theory. I'd like to begin by explaining why quantum mechanics is such an important subject, both in physics but also in mathematics. Quantum theory forms the foundation of all modern theories of physics, along with Einstein's theory of relativity. In fact, these two theories underpin essentially all of theoretical physics that's been developed over the last 100 years or so. Quantum theory successfully describes the structure of matter, what everything in the universe is made of. We have enormously successful quantum theories of fundamental particles, so things like electrons and photons that we'll meet a little bit later in the lectures. Those theories also explain how fundamental particles fit together to form atoms, how atoms fit together to form molecules, and consequently explain the structure of solids, liquids, and gases. We also have quantum theories for all known fundamental forces that act between particles, with one exception, namely the force of gravity. It's also worth mentioning that quantum theory led to enormous technological advances in the 20th century. Perhaps two that are worth mentioning are the laser and also the microchip. We wouldn't have computers and mobile phones were it not for the development of quantum mechanics earlier in the 20th century. Quantum theory also leads to some beautiful mathematics. Entire branches of pure mathematics developed out of quantum mechanics in the 20th century, particularly in the areas of analysis and algebra. Familiar dynamical quantities, things like position, momentum, and energy, will take entirely new mathematical forms in quantum theory. And along with those new mathematical forms will be new physical interpretations of those dynamical quantities. And it's here where quantum theory is famously counterintuitive. It leads to some quite deep philosophical questions about the role of the observer, what it means to make a measurement, and even the nature of reality itself can be quite counterintuitive in quantum theory. We'll begin the course by explaining that classical physics, by which I mean Newtonian mechanics that you studied in the prelims dynamics course last year, fails at the atomic scale. Newton's laws simply don't apply to things like electrons and atoms. And we'll begin by describing some key experiments that demonstrate this. These were experiments that were first performed at the end of the 19th century and beginning of the 20th century. One final point that's worth making is that one cannot derive quantum theory. Instead, we'll motivate the key ingredients, and then in the course we'll focus on the mathematical structure of quantum theory and the formalism. Section 3 of the course is called the Born interpretation. This isn't the name of a Matt Damon film. Instead, it's a physical interpretation of the wave function that appears in the Schrödinger equation. So we've now met the Schrödinger equation and solved it in the simplest example, namely a particle confined to a box. We've also shown that the possible energies of that particle are quantized. That is, they take values in some discrete set, and moreover are naturally labelled by an integer n. What though is the physical meaning of this wave function psi of x and t that we're solving for in the Schrödinger equation, and in particular what's the relation of that function to the position of the particle? To motivate this, we're going to go back to the double slit experiment that we looked at in section 1 of the course. So let's remind you of the setup. So we have a double slit configuration here in the center. That's just a screen with two small holes cut in it. We're then going to fire a beam of electrons from the left at this double slit configuration. And on the right hand side, there's a detector screen to detect where the electrons hit. That's a phosphorescent screen, and if an electron hits a particular point on that screen, we'll see a small dot of light. Imagine then that we've sent lots of electrons through the double slit already, say 100,000. what we'll find is that electrons tend to hit certain parts of the screen more than they do other parts of the screen. We can then plot that as a density function, and that's what I've done here in the picture. So for example, at the peak here, opposite there, more electrons tended to hit this point than they did opposite a trough, which is here. That density function then remarkably gives the form of a diffraction pattern. We're next going to make two key observations. Firstly, imagine that we send another electron through the double slit configuration. Where is it most likely to hit the detector screen? Well, it's more likely to hit an area of the detector screen where lots of electrons have already hit the screen, and it's less likely to hit an area of the screen where very few electrons have hit the screen. In other words, we can interpret the density function that I've sketched here on the picture as a probability density function for where the next electron will hit the screen. That's the first point. For the second point, imagine performing the same experiment, but now with light. That's called Young's experiment, and you might have seen that before, for example, if you studied A-level physics. In that case, the diffraction pattern that I've sketched here in the picture is interpreted as the intensity of the light that hits the screen. So opposite a peak here, there'll be a brighter patch of light, and opposite a trough here, there'll be a dimmer patch of light. Now, it's then a standard fact from optics that the intensity of light that you measure is given by the absolute value squared of the amplitude of the wave that's describing that light. This would have been a fact that was well known to the pioneers of quantum theory at the start of the 20th century. It's quite easy to give a fairly intuitive description of why this is true, though. So remember that for waves that constructively interfere, those will have a bigger amplitude, and then we're just saying that that will correspond to a brighter spot on the screen. On the other hand, waves that deconstructively interfere with each other will have a smaller amplitude, and that will correspond to a dimmer spot on the screen. We're then going to conflate these two observations. So remember that the electron is going to be described by a wave function, satisfying a wave equation, namely the Schrödinger equation. And it was Born who postulated that the probability density function for where we find the electron, that's rho of x and t, is given by the absolute value squared of its wave function, satisfying the Schrödinger equation. In other words, this function that we've been solving for, psi of x and t in the Schrödinger equation, is actually giving us a probability density function for the position of the particle. We can rephrase that in the following equivalent way. So suppose that we've got some region, capital D, which is a subset of R3. Then what we're saying is that the probability of finding the particle in that volume is given by an absolute value squared of the wave function of the particle over d. Here d3x in the formula is short for dx, dy, dz. Notice that this probability depends both on the region d that we're integrating over, but also on the wave function psi of x of t that's describing the particle. Moreover, to make sense, the probability of finding the particle somewhere in R3 had better equal 1. That then leads to the following definitions. So we say that a wave function is normalizable if the absolute value squared of the wave function integrated over the whole of R3 is finite, and will also require it to be non-zero for all times t. A wave function is then said to be normalized if the integral of the absolute value squared of the wave function over R3 is equal to 1 for all time t. The normalized condition here on the wave function is necessary for the probabilistic interpretation of Born to make sense. There are fairly obvious similar definitions for motion in one dimension. So for example, for a particle that's moving on the x-axis, then the absolute value squared of the wave function integrated over the x-axis between minus infinity and infinity should equal 1. Let's then make some remarks on what we've said so far. Firstly, the Born interpretation says nothing about where the particle actually is if we do not measure its position. This is very different from classical mechanics, where the position vector of a particle is always well defined. In particular, vector x of t in classical mechanics satisfies a differential equation, namely Newton's second law. This is not true at all in quantum theory. For example, if we go back to the double slit experiment with electrons, for a classical particle we'd ask which slit did the electron pass through. For a classical particle, its position is always well defined, and that's a well-defined question. But in quantum theory, the position of the particle is only defined if we measure it. So it doesn't make sense to ask which slit the electron passed through. Its position is not defined unless we measure it. This is one of these examples of very counterintuitive reasoning that appears in quantum theory, and we're going to have to change some of our classical notions of even basic ideas such as position of particles. Secondly, the normalized condition fixes the freedom to multiply a wave function by a complex constant. So remember that the Schrödinger equation is a linear equation, and we can always multiply any wave function by a constant, and that will still be a solution. That freedom is fixed by this normalized condition here that I've written at the top of the page, but it fixes it only up to multiplying by a constant phase, e to the I phi, where phi is a real number. So that phase is a unit norm complex number. It's then a postulate of quantum theory that wave functions that differ by a constant phase such as this should be regarded as physically equivalent. It's a little bit like the freedom in classical mechanics to shift the potential energy function by an additive constant. That drops out of the force that's acting on the particle, and so is simply not physical. Lastly, let's look at the wave functions for a particle in a box that we've solved for. Here, psi n of x and t denotes the stationary state wave functions that we solved for, where n, remember, was a positive integer. And we're going to integrate the absolute value squared of those over the real axis. The wave function, remember, was identically 0 outside of the box, so we just get an integral here between 0 and a. The wave functions were proportional to an integration constant b, so I get the absolute value of b squared outside the front here. And then we integrate sine squared n pi x over a between 0 and a. So remember here, the Fourier modes sine n pi x over a, we're giving the stationary state wave functions inside the box. If we do this integral, we get a half a times the absolute value of b squared. That's finite, so the solutions are normalizable, and moreover they will be normalized if we take b, the integration constant, to be square root of 2 over a. This integral then is equal to 1 for all of the stationary state wave functions labelled by n. Moreover, remember that we said that we took the wave function to be 0 outside of the box, and I promised that I'd come back and explain later why that's the right thing to impose. We can now see why that's the case. So for a particle to be confined to a box, that means that the probability of finding the particle outside the box must be 0. But that precisely means that the wave function should be 0 outside of the box. For a stationary state of energy E, we can calculate the probability density function rho of x of t. Well, that's given by the absolute value squared of the time-dependent wave functions, that's capital psi of x of t. For a stationary state, though, those take a product form, where we get little psi of x, giving the spatial dependent part, times a time-dependent factor, which is the usual form of e to the minus iet divided by h bar. That time-dependent factor, though, is a unit norm complex number, so we see that the probability density rho is just the absolute value squared of psi of x, and in particular that's independent of time t. If we then normalize the stationary state wave function, little psi of x, then the full time-dependent wave functions, capital psi of x of t, will be normalized for all time t. Finally, recall that we started our discussion of the Schrödinger equation by looking at the complex plane wave. So to remind you what that is here, that's where psi of x of t is given by a constant amplitude, capital A, and then we have e to the I vector k dot vector x. So vector k here is the wave vector of that plane wave. And then we have a time-dependent factor, e to the minus I e t divided by h bar, where E here is given by the classical expression for the kinetic energy of a particle, namely p squared divided by 2m, where we've used the de Broglie relation that the momentum p is equal to h bar times the wave vector k. This complex plane wave satisfies the Schrödinger equation with potential energy function v equal to 0, and physically it's interpreted as a free particle, so no forces acting, with momentum given by vector p equals h bar times the wave vector k. What we notice, though, is that this complex plane wave solution is not a normalizable solution to the Schrödinger equation. In particular, the exponential factors here are unit norm complex numbers, so the absolute value squared of psi is just given by the absolute value squared of the constant amplitude, a. But that's not integrable over R3 unless a equals 0. The wave function for a free particle then is not normalizable, and in fact there's a very good physical reason for that we'll come back to explain later in the course. Let's now look at some examples of calculations using this probabilistic interpretation of the wave function. And to do so, we'll go back to our example of the particle in a box, 0a. So firstly here I've written down the probability density functions for the stationary states. Remember, those are labelled by a positive integer n, so this is rho n of x. And here that's equal to the absolute value squared of the wave functions inside the box. So that's 2 over a, where I've used that we fixed that normalization constant b to be the square root of 2 over a. And then we get the Fourier mode squared, so sine squared n by x divided by a. And it's convenient to use a double angle formula to express sine squared in terms of cosine 2 n by x over a on the right hand side here. These are the probability density functions for the particle in a box inside the box. And remember that the wave function is identically 0 outside the box, and then so is the probability density function. I've then plotted those probability density functions for n equals 1, n equals 2, and n equals 3 in the pictures below. Notice that these probability density functions have some wave-like characteristics. There are peaks and troughs, just as we got in the double slit experiment when we looked at that density function for where the electrons hit the screen. We can introduce other standard concepts in probability theory. So, for example, we can introduce the distribution function. That's the probability that we find a particle in an interval 0 up to x, where x here is between 0 and a. So by definition, that's capital F subscript n of x, n labelling the stationary states. That's equal to the integral of the probability density function rho n of y integrated from y between 0 and x. If we do that integral, we get x over a minus 1 over 2n pi times sine 2n pi x divided by a. I'd like to remark that the first term on the right-hand side, x over a here, is the result for the uniform distribution. The uniform distribution is where you're equally likely to find the particle anywhere inside the box, i.e. the density function in that case is just constant. We can interpret that term as the result for the classical particle. So by that I mean the following. Suppose that you're ignorant of the initial state of the classical particle. So at some initial time, we don't know where that particle is inside the box. Since the particle just moves back and forth across the box with constant speed for the classical particle, it's then equally likely to be found anywhere inside the box if we measure its position. So the first term here is, in some sense, the result for the classical particle given by the uniform distribution. The second term, with this 1 over n factor here, is called a quantum contribution or a quantum correction to the classical result. Let's look at an example of calculating a probability using this formula. So the probability that the particle is in the region a over 4 up to 3a over 4 is given by, well, we just integrate the probability density function between those two values. By definition, that's equal to fn of 3 over a over 4 minus fn of a over 4. And using the formula for fn above, that's equal to 1/2 plus 1 over n pi times sine n pi divided by 2. In particular, notice that this quantum correction term here, proportional to 1 over n, tends to 0 as n tends to infinity. In other words, as the quantum number n tends to infinity, the result of this calculation approaches the classical answer of 1/2. This is the right answer for the uniform distribution because the region that we integrated over here is half the width of the box. There's something then called the correspondence principle in quantum theory that asserts that quantum results of calculations tend to approach those of the classical theory for large quantum numbers. It's hard to make this statement very precise because there's no general definition of quantum number in quantum theory, but we'll see a number of different examples of this throughout the course. We can also introduce some further concepts that are standard in probability theory. For example, we can compute expectation values. So here's a definition. The expectation value of some function of position, f of x, in a state capital psi for the particle, so psi here is the wave function of the particle, is given by just integrating f of x over R3, where we weight that integral with the probability density function, which is the absolute value squared of the wave function psi. This is exactly how you would define expectation value for f of x in probability theory, with the absolute value of psi squared here being the probability density function. For example, for a particle in a box, we can calculate the expectation value of the particle's position in a stationary state. So here the stationary state is psi n, and we're calculating the expectation value of x, the particle's position. That's an integral between 0 and a of x times the probability density function, rho n of x. And if we substitute in the formula for rho n of x that we had earlier and do the integral, you get the answer of 1/2 a. Notice that that's independent of n, the quantum number in this case, and moreover it agrees with the result for the classical uniform distribution. So for the uniform distribution, the particle is equally likely to be found anywhere inside the box, and moreover its expectation value of its position is then the centre of the box, a over 2.